Welcome to video number 6 in Microfluidics. So today we're going to be continuing on from where we left off last lecture, and we're going to do one more exact solution here. And this one's really interesting because we're going to sort of probe some of the things that happen when we non-dimensionalize and scale these equations. We're going to take a look a little more deeply and see how that influences our solutions. So I've listed this here as problem 4.2. So we're saying it's the startup of a two-dimensional channel creeping flow. So we previously obtained the equation for Stokes flow, and I'll write that out here. That's just a zero with a bar over it, right? So we remember this is actually a vector. By non-dimensionalizing the time by the characteristic time scale, L over U. And this normally makes sense. So I've written here, in a typical flow, this makes sense because L over U describes the time it takes to cross a distance, L, when you're moving at an average speed, U. And so that's normally the scaling that makes sense for us, right? But sometimes in problems, there can be things that go on faster than that, right? So if there are, for example, I have oscillation of a boundary there. So if things are occurring more quickly, right, than this scale L over U, we have to make sure we factor that into the equation, but we've neglected the time derivative, right, with our non-dimensionalizing. So we say in those cases, we cannot neglect the time derivative term of the Navier-Stokes equation, right? So in that case, if we wanted to have our solution pick up on these things that were happening very quickly, okay, we would have to have the time in the equation. Okay, so now we're going to take a look at how do we build this in. So we would need to rescale the time t with some characteristic response time of the fluid, we're calling it there. Okay, and this scaling, so rho L squared over mu, that's the time it takes to reach steady state. And we can probe this a little bit. So this response time factor here, I'll just make a little note above it here. So when we look at the mu term, right, as mu goes up, response time goes down. And so that's as the fluid's more viscous, right, it's more resistant to shear. So the response time is longer, okay? And then we see density is on the top, right? So as density goes up, response time also increases. Okay, and that's because the forcing on the fluid increases. So as density goes up, it responds more quickly as well. So its response time goes up as well. All right, so let's start by writing out our momentum equation again, and then we'll non-dimensionalize that. So here we go. I'll use a different color for our dimensionless variables. I was asked before about the del operator there. So it simplifies the process if I just kind of write out the del operator there, and those bars above it mean it's a vector. Well, it's an operator, so I guess it's not officially classified as being a vector or not a vector. So don't worry about that, whether you see it as a vector or not. Just remember that anytime you substitute in for the dimensionless del operator, you use L times the del operator that has dimension. And then time, as we mentioned, we rescale differently. Okay, now let's see what happens when we do that, okay? This is, as I mentioned, this is actually really interesting. So again, we've done this substitution a number of times, so I'll go ahead and do that here. On the line below. Okay, so right off the bat, I'll use again another color here. I can simplify, right? So we've got some easy ones there, and then I'll go ahead and regroup this. I'll get a fresh page to do the regrouping here. Make sure I'm recording this time because I didn't do it last time and I had to rewrite it. Okay, so I regroup with our new scaling as follows. So what happens is it looks like this. Okay, and remember the del, it's an operator, right? So the del squared as well. So when they have the primes on them, they're just the dimensionless versions of the operator. And whether they're a vector or not, it just depends on what they're being applied to, right? Okay, so with this regrouping, we see now that the Reynolds number is here, okay, importantly only there, right? So now we go again, we say we're interested in low Reynolds number flows, right? So as Reynolds is really low or approximately 0, we end up with the following equation now. So I'll just use a different color, and this whole term, when Reynolds is low, we get rid of that whole term this time. So what does that leave us with? Alrighty, so that looks like this. And I'll just make a note here. So that is representative of low Reynolds number time-dependent flow. Okay, so we're in place of the Stokes equation. Let's solve with this equation and see what happens. So we've kept time dependency. As we mentioned earlier, that was our goal. Okay, using our new scaling for time. Okay, so we're gonna go ahead with our exact solution now, right? This lecture is about the exact solution. So we're gonna employ a geometry again. So for simplicity, we're gonna use the following geometry. We mentioned it's 2D, but we saw last time, like along the width of the channel, we can negate the dimension in the width direction. So in this case, we'll just flat out use 2D. So we're gonna say for simplicity, again, we're taking the approach of microfluidics here. So this is a very common geometry, as we've seen, right? Channel like this, and we're gonna use the same coordinates that we've been using, keep things consistent. So y is up, x is across, and then we remember that we have our height, and in this case, we will define it from the midline to the top. So half of the total channel height, we're gonna call that h. Simplifies our problem later, boundary conditions. So it's just easier to do it that way. Now, the boundary value problem that we have is the following. And so we've made a lot of simplifications from the boxed equation above, right? And we did that. So if you want to see the details of that, look back to the previous lecture, right? So that went from a vector form into only the x direction here that we've kept. And we made a number of other simplifications using, for example, the continuity equation, etc., to simplify down to this form. Okay, so I'll just write here, like based on the earlier analysis, we can see how we simplify down. I'm not going to do it again, because you've seen it already. So we know how to get it into this simpler form based on what we did last time. Okay, let's go to a fresh page. I'm gonna write out the corresponding initial conditions and boundary conditions for this. Okay, I wanna have the complete boundary value problem here. So I'll just rewrite that again. Okay, so that initial condition tells us that initially the flow is stopped, right? Because we're solving for startup of the flow. So we'll say initially it's stopped. Okay, that's the initial condition there. That's along the wall. That's the no slip condition. Again, symmetry along the center line there, the y0 location. Okay, now same as before, we're gonna say let the dp by dx be a constant g. And that reminder, so this is normally like a pressure driven flow. So that pressure gradient tends to be what drives the flow. So that's something normally that's applied, right, to a microfluidic system or a microfluidic channel like this. Now we're gonna go ahead and rescale this. For the physical system we have here, so h is our length scale, and we have this pressure-driven velocity scaling, and that's the scaling that we use for time. As we mentioned previously, we want this characteristic time to be kept in now so we see the time dependence. So we scale it the same way. Go ahead and sub these in yet again, and I'll do the simplification here of everything subbed in because we've seen this a number of times now, and do it in assignments yourself as well, which is where the learning kind of really gets cemented. Okay, now that very nicely simplifies to the following, right? The initial and boundary conditions, the new ones here in a different color at the side. I want to keep it all together as much as possible. Okay, this is what we're solving now. And we've seen equations like this before, hopefully in calculus, but I want to go through the entire solution here because I think it's interesting to see how we can actually analyze the solution that we get so we actually see what it means in a question like this. It's really quite interesting in this problem. So I'm just going to make a note here. For the sake of simplicity, I'm not going to use the primes and subscripts anymore. This is, again, like a common trick you do when you're doing a non-dimensional analysis. You don't want to keep writing the primes the whole time, frankly. So I'll just make a note that we're going to, from now on, they're still there, right? But we're not going to write them for simplicity's sake. And the subscripts, oh, just noticed a mistake on that, of course, that. I'll just fix that one there. Good thing I caught that. You just noticed that was like a obvious mistake copying down from the line above. Drop the primes and the subscripts for the solution. As we move forward, no more primes, no more subscripts, okay? Now I'm gonna need a fresh page for this. Okay, now the strategy we use to solve this is we're gonna find the steady state solution, and then we're gonna solve our boundary value problem using the difference, so our u minus our u steady state with separation of variables. So I'll make a note of that here. And a reminder, like steady state solution means we don't have any time dependency, right? So that would mean like we don't have any of this time dependency anymore. Okay, so rewrite this for our steady state solution where we don't have the time derivative anymore. So that's this with these corresponding conditions. US is a function of y only, so we can just actually integrate this now. We can write it as a ordinary differential equation. You don't need the partials anymore because US is only a function of y. So as we go down, then we have, and that is because, right, C1 equals 0, right, with this condition applied. And then let's use our boundary condition to get C2. So I will write that out in green. right? So we're saying it's equal to 0 when y is 1. Therefore, C2 equals a half. From there, just to make it clear. Alrighty, that takes care of the steady state solution. So that was not too bad, hey? Alrighty, now I'm gonna do transient solution, so we'll take a fresh page for that. Okay, so we say we let our full solution be our steady state solution plus the time dependent portion. Now we substitute that in to the problem that we're solving. Substitute like this that I'm underlining, the right-hand side here, and you end up with the following. Okay, and based on our solution above, right, so this has no t dependency, that goes to 0. This, we've just seen, is equal to -1. So then we apply those simplifications from that, and we end up with this equation here that we have to solve for with the following conditions. I'll use a different color for that. Remember now, right, like we're solving the condition has to be true for the u function that we wrote above, and u is actually us plus ut, right? So when we sub in, our u boundary conditions have to match now, so that is half y squared minus 1. Okay, now that works out for us because that is a homogeneous PDE with homogeneous boundary conditions. And we can solve that with separation of variables, actually. Okay, so let's go ahead and do that. Now just rearrange this here, and then we can use a trick that we've used before. So if we split the two sides with their functionality, right? So we see what's happened here again, left and right-hand side, only t, time functionality on the left, only position y functionality on the right. So we have this situation again where the only solution is if both are a constant. Alrighty, gonna need a fresh page for that. All right, so that is our constant. We've assigned this constant here. Now we break this apart. This might look familiar to you. I think if you've had calculus as an undergrad, right, or even as a grad student, this is sort of a classic solution. So we'll go ahead and break apart for t first here. Okay, and again, we can recognize the form of that. So that's a classic solution. And I'm sure there's lots of refreshers you can have on this, but this isn't a calculus course, right? So we're just gonna go ahead and write out the solution here. Now let's look at y. Classic general solution, our periodic solution there. Write out the boundary conditions here so we can get those constants, right? Okay, so we sub in directly for this boundary condition, right? And only the y portion has the y functionality, so that keeps the derivative on that side. And then we see, so we don't want t to be 0, so to make this 0, we're gonna have the dy by dy term be 0, therefore b has to be 0, right? And I've skipped a few steps there, right? So this is we're saying the derivative at 0 is equal to 0. So we would have, from our y solution here, the a and the b would then be multiplied by the sine and then the cos. So the b has to be 0 because the sine at 0 is already 0. So we can keep the a term there. So that takes care of our b constant. Let me use a fresh page here for the next one. Okay, second boundary condition. That leads us to an eigenvalue condition. So that cos function will be equal to 0 when we have the following eigenvalues. So that ensures that that function equals 0. So then by superposition, we can get the transient portion of the flow here. Okay, now we can use our initial condition to do our final simplification on this here. So that's what we had. We wrote this above there. And now we're going to apply it. And so what we do with eigenfunctions is we apply orthogonality to get our constant a subscript n. And again, so this is probably too tangential for me to go into all these things, but you can have a look at orthogonality. It's actually a pretty sweet trick for these kind of functions. So I'll make a note of that here. Okay, then you go ahead and you solve that integral. So you could solve it by hand if you want to. You can use software, Mathematica or Maple is what I generally use for these things. So we solve out that integral. Now we can get what our a sub n term is going to be. I need a fresh page. And we're almost done here. So that's the last fresh page I'll probably need. So we can go say that we solve this. And that is what you get. Okay, so therefore, we have our solution now, right? Taking care of all our conditions. Benefit of using the wider slide here to write on is I can hopefully fit this all in if I'm careful, subbing in everything, right? And then that gets boxed, of course. That is our solution there. All right, and we just reflect for a quick second on why it's so much more complicated to include the time, but still possible to get an exact solution in this case. Now we're going to go ahead and look at this solution. Okay, so that solution looks like this, and I'm going to label this again. So this here is y prime, and what I've done, let me do this axis first. So this is like our ux prime, and what I've done here is plot for a number of different values of t prime. So this one here is t prime 0.01, this is t prime 0.1. Green, I use t prime 0.3, red 0.5, and finally t prime equals 2.0. And we can see we're almost at steady state there. So our steady state is actually half, we can see from our solution. And so basically we're there at 2 prime equals 2.0. But what, so we have scaled this, right? So that's a dimensionless time equals to 2. Okay, so I think it's kind of cool to see what time is that, right? So again, what's plotted here, right, is the startup of the flow. Okay, so we started stationary, and then we moved through these t prime timescales, right? And we see the flow go from the stationary into its full velocity profile by t prime equals 2. What is t prime equals 2? So let's scale. That was scaled like this, right? So let's go ahead and sub that in, right? For like a classic problem. So we'll say 1,000 kilograms per meter cubed, just like water. 10 times 10 to the minus 6, classic microchannel. And that is squared. And our viscosity, subbing in these values for like our classic microfluidics problem here. As you sub these in, right, it's always good to check the units. So a Newton is actually kilogram meters per second squared. So this whole unit here simplifies to kilograms per second meter, which cancels from the top, which is kilograms over meters as well. So they cancel. We're left with seconds, which is on the top, which is what we need. Okay, so we're at 0.0002 seconds. Okay. Excellent, right? Because we said that time doesn't matter. And so we can see if we have something that's so insanely fast that we need to see within 0.0002 seconds, right? That's what the startup flow would be. But essentially this flow hits steady state in 0.0002 seconds in a classic microchannel. The dimensions with like a water-like fluid. Okay, so that there you go, right? So that's what would happen. So and I noted at the bottom there, since the flow is reversible, the solution also tells us how the flow will stop if we suddenly remove our pressure gradient. And so you can see why, essentially, right, we're never going to care. Nothing is that fast, right? So normally we just get rid of the time dependence. That's why we can get rid of it. So this is, again, an example that shows, hey, we can get rid of it. Totally fine, because it stops and starts so quickly. You'd never be able to see that, 0.0002 seconds. But what's fascinating, right, is like if you did have something within this flow oscillating very quickly or that was capable of moving like incredibly fast in these small time scales, then you would have to actually consider time, right? And so this gives us I think it's really cool, right? We can see the time dependency in a problem like this. So it actually does have this evolution of flow. It just happens so fast, 0.0002 seconds, and we're not concerned with it unless we have other things also happening at this sort of time scale. All right, so that's it there. That's our exact solution. Next time we're going to be going on to the transport equations. So we're going to look at diffusion and Brownian motion. And so yeah, I'll close just by summarizing this. So what we did an exact solution right, in this lecture as well, just like the previous lecture, where we used everything from before, so all the equations and non-dimensionalization we had done. And in this case, we actually kind of probed, so we went back and looked at what if we leave time in to these equations, and we just saw, for startup flow, like exactly how quick that happens and exactly how you would sort of include things that had time dependency at these very, very short, very quick time scales, right? 0.0002 seconds. Okay, so that's all for video number 6. Thanks for watching.